Hey everybody, and welcome back to I Hate Chemical Engineering. This is going to be a recap of our first 5 videos through Thermo 1. So again, we're going through the Introduction to Chemical Engineering Thermodynamics 7th and 8th editions by Smith, Van Ness, and Abbott. So let's go ahead and just go through it. I wanted to do a recap because, again, you try to learn concepts in like a logical order in thermo, but unfortunately, sometimes it's like you kind of need to know everything at the same time in order to understand it holistically speaking. So let's just go over what do we know now. So let's say, what do we know now? And let's make a list. And I would encourage you all to do this too, because it can serve as kind of an equation sheet if you all have tests, or kind of a cheat sheet just for you all in the private of your own careers. So first off, let's talk about the Gibbs phase rule. So the Gibbs phase rule, again, was a way for us to determine how many degrees of freedom. So F is the, I guess, official variable for degrees of freedom. I was using DOF in the previous video, but it's going to be 2 minus pi plus n, where pi is the number of phases present in the mixture, and then n is the number of components in the mixture, right? So what does this tell us? So F tells us how many variables, state variables, need to be specified in order to fully define the system. Why is that important? Because in future classes, we're going to go over how to be able to calculate those other state variables. And if we have a pressure and a temperature, or we in particular to like maybe a distillation column, you got an enthalpy balance going on between the systems, you're able to calculate the rest of the state variables, given that the number of variables as specified by the Gibbs phase rule. So that's going to be important, and I think it needs to be at the forefront of your mind, at least in understanding of this course, is that thermodynamics is going to allow you to be able to specify and fully define the system with a minimum amount of starting information. So the most basic thing that we're trying to accomplish in thermodynamics is the energy balance, right? And you all learned a lot about that in heat and material balances, or whatever course, Felder-Rousseau course that you all have had up to this point. But the general energy balance is going to be the change in total internal energy, which is mass times internal energy, or specific internal energy, or molar internal energy of the system, is going to be equal to the negative change in the mass flow rate in versus out of the system, the enthalpy change in versus out of the system, the kinetic energy change in versus out in the system, the potential energy change in versus out in the system, plus the heat rate into the system, plus the work rate done on the system. Right, so this is the fully defined energy balance for our system. Now, this doesn't take into account, heat changes, as a result of reactions. This is taken solely into account changes in internal energy as a result of heat and work, plus the flow streams and the energies that those flow streams have. So again, those bracketed terms had to do with the flow streams going in and out. And then the dotted terms, the Q and the W, has to do with the kind of the we called it the non-physical or flow stream transfer of energy. So, to be specific, we have a closed system balance that's simplified down to the change in internal energy is going to be equal to the tiny, the differential amount of heat added to the system plus the differential amount of work done on the system. And then we had another one that was for the open system at steady state. And that means, since it's at steady state, that the internal energy of the control volume is assumedly not changing. So we end up with the change in the mass flow rate, in versus out, times the change in enthalpy, the change in kinetic energy, the change in potential energy is going to be equal to the heat rate plus, and usually we simplify this to the shaft work at this point. Then we, in the following video, we defined, for the sake of being able to define heat capacity, we defined compression and expansion work. But basically that says that a control volume can do work on the environment without the need of a shaft, right? And that work was going to be equivalent to, the differential work is going to be equivalent to the negative pressure as a function of volume times the differential volume. And again, I emphasize that it's as a function of volume because though, the pressure might be in some way independent of volume, it's likely not constant with respect to volume unless you have a very specific isobaric system, which we'll talk about in future videos. Almost forgot, we also talked about the definition of enthalpy, right, which is going to be equal to H equals U plus PV, which helped us, in our definition of flow work, right? So we had flow work was PV, and that's part of the flow streams going into the system. Internal energy is U. So U plus PV equals enthalpy, and that's why we use enthalpy on in the energy balance. So, and then in the final video, we covered two different kinds of heat capacity. So we said, in general, heat capacity, by definition, is the amount of energy needed, and then I think you can call that energy in the form of heat needed to raise the object's temperature. We'll say the matter's temperature by 1 degree C, and you do that on a kilogram basis, right? So so we'll say per kilogram. And we talked about how in fluids that there are two kinds of heat capacities that we were concerned with typically. So we have the constant volume heat capacity, right? And we said that definitionally that the constant volume heat capacity is always going to be equal to the change in internal energy with respect, the partial derivative of internal energy with respect to temperature at constant volume. Now, that might seem fairly obvious, but what it works out to is that when that when certain situations occur, such as an ideal gas, or in other words, when the partial derivative of u with respect to volume at constant t equals 0, you have an exact relationship, but in general, an approximate relationship between the internal energy and temperature. So du is approximately equal to CV dt, and at constant volume, you always have this relationship. I shouldn't say always the dq CV dt part, but at constant volume, that's what you end up having, is du is going to be equal to CV dt. Similarly, we had a constant pressure version. And I'm going to actually fix this right here because this will come up later. So forgive me. So d equals CV dt, and it probably equals dq. And we say probably because we didn't talk about reversible or irreversible processes, but we did talk about how the q is path dependent. So we'll cover what that means more in later videos, but in general, this is what we're talking about. So, but for the constant pressure heat capacity, similarly, we have the change in enthalpy with respect to temperature at a constant pressure is always going to be equal to the constant pressure heat capacity. Similarly, the differential change in enthalpy is approximately equal to the constant pressure heat capacity times the differential temperature. And in particular, it's true if it's an ideal gas, or any time where dH, or the partial derivative of enthalpy with respect to pressure at constant temperature, is 0. Or, when the pressure is constant, right? Right. And that, again, is going to be equal to dq, or approximately at least equal to dq when the pressure is constant. So, yeah, so I know that was a very short recap, but I think this is going to give you everything you need to be able to follow along in the next couple of examples, guys. So, if you enjoyed that recap and found it informative, please like, comment, and subscribe. Thanks, guys.